we've kind of actually, by finishing up this section 15.2 on limits, we've sort of done the heavy lifting for much of the rest of chapter 15, and also for much of chapter 16. And so what we're going to see is that once we have the notion of limits, we can develop various notions of derivatives. We'll see what we mean by that as we go forward. And we can also start talking about other forms of integration. And what we'll do is we'll just say, hey, let's look at these new ideas under the lens of Calc 3, but using our insight from Calc 1. So it's kind of been a slow start getting started into this chapter 15 and chapter 16 material, but now that we've got the idea of limits, we're ready to hit the ground running. So let's look at this example here. And we've got some terrain here, and you can see that this terrain in image B is being represented here in image A in a three-dimensional coordinate system. And let me just ask you the question. So here we've got the hiker, and he or she is standing right here. By the way, there's a name for the place where the hiker is standing, and it works both for math and for hikers. Both mathematicians and hikers agree as to what to call the point where that man's standing. What do you guys call that? Do you know?
Saddle?
It's a saddle. And so maybe you know that from your outdoors, or maybe you know that from your indoor math exploration. I don't know which one. Okay. But here we have a man standing in a saddle, or a hiker. I don't know the gender. And as you move away from this point, let me ask the question. Are you increasing or decreasing in elevation? If you move away from where you're currently standing, are you going to increase in elevation or decrease in elevation? And don't...
Depends what direction.
Yeah, let's not try too hard with this. It depends on which direction you're heading, right? And in fact, as we've oriented this coordinate system here, notice, so today what we're going to explore is we're going to explore moving along either the y-axis or moving along the x-axis and answering the question, as we move along the y-axis, how is our elevation changing? And for this particular surface that has a saddle point in it, by the way, we saw saddle points in our hyperbolic, was it hyperbolic parabolas? Parabolic hyperbolas? I can't remember. I'll have to get back to you on that. I don't have it at the top of my head right now. But we saw these curves, we saw these saddles appear in some of our surfaces already. Okay? And so if I'm heading along the y-axis here, leaving the saddle point, heading along the y-axis, we would see that as I go in the positive y direction, my elevation is going to be decreasing here. Okay? So even though we don't even have this notation yet, let me just go ahead and say how we're going to denote that in a minute. We're going to say that the change in elevation as we move in the positive z direction is negative. So I'm introducing this symbol here. We're going to look at it in just a second, but if you're, let's just let the cat out of the bag. We'll call that the partial derivative symbol. And so you would read this as the partial derivative of z with respect to y would be a negative quantity here. Let's focus on the notation here in a minute. Let's put the notation aside for just a moment. And let's just focus on the idea here. If you're this hiker and you're moving along in the positive y direction, your elevation would be decreasing, and so we would say that your rate of elevation change in the y direction is negative. Okay? Whereas if we look at our change in elevation as we move along the x-axis in the positive x direction, we would expect that to be what, folks?
Positive.
It's positive. Okay? So how do you read this? You would read this as the partial derivative of z with respect to x, and right now all we can say is that it's positive. But you should agree with that looking at this, this image of the hiker, right? If the hiker heads east, the hiker will be heading uphill. That's conveying the same bit of information as this mathematical statement is when we think of it as being in the three-dimensional coordinate system. Questions on just let me just say, any questions? So we're going to return to the idea of computing the slope of a tangent line that we did way back in Calc 1, and we're going to redevelop it, but we can't talk about taking the derivative of this surface. That really doesn't have a meaning to us, okay? We will talk about what it means to be differentiable in a little bit, and that will have some meaning. We'll say what it means to be differentiable. We'll also say what it means to take the derivative with respect to a particular direction. And we'll have some other notions of derivative. So one of the things that I want to caution you about is that, there's always these parallels or these sort of similar ideas in Calc 3 to Calc 1, but they're not a perfect carryover. Things don't carry over perfectly here. So what we'd like to do is we'd like to think of this point here. We've got the ordered pair. Here we've got the ordered pair A, B, comma, f of A, B, right? It's an ordered, sorry, I said ordered pair. It's an ordered triplet where we're given some x coordinate A, some y coordinate B, and that spits out some z coordinate f of A, B. Okay? So what we'd like to do is we'd like to think of taking a slice through this curve. We're going to take a planar slice through this surface here, okay, so that we're parallel to the x-axis. And you can see the drawing here. We've got this planar slice through the surface that's parallel to the x-axis. Why is that beneficial to look at that particular slice? Because if I look at different points along here, this might be some, in fact, I'll go ahead and label it. This might be some a plus, I'll say, a small change in x. And that's going to give me a different z value, right? But what coordinate's going to remain the same if I'm taking this from a planar slice that's parallel to the x-axis? What coordinates?
The y coordinate.
The y coordinate's going to remain just as it was b, so it's going to remain b there. And then the z coordinate then is just going to be this new x coordinate, so f of a plus delta x, comma b. But notice that the y coordinate in both when we look at the y coordinate, I guess in the order triple, but then we look at how we compute the z value for our function, that hasn't changed. Okay. So that enables us to compute the slope of a secant line, and we're just drawing this picture here. I'm not going to do any more than look at, and here they're using h instead of delta x. So you don't have to change this, but just for consistency with the diagram, I'm going to call it a plus h, and we'll call that a plus h here. Okay. And so here we're computing the slope of the secant line the same way we computed it in Calc 1, but we're restricting our attention to the plane where y is equal to b. So let's just say that's the plane y equals b. We're restricting ourselves to that plane. And so even though y is an independent variable of this function, if we intersect the function with this plane, y does not change along this curve that's created by that intersection. Okay. And so here you can see the analog to computing the slope of the secant line between 2 points. So you would take this height minus this height divided by the change in the x coordinates. Okay? So I want you to, this still looks sort of something like, y2 and y1 is maybe misleading, but let's just say this looks like a slope formula. Okay? That is, we've got one ordered pair. That's a z coordinate, but so let me say we're looking at a slope formula this way. We're looking at it as some z2 minus z1 all over x2 minus x1. That looks like your original slope formula, right? But instead of writing z2, we're writing f of a plus h comma b, that's the second z value, minus f of a comma b, that's the first z value, all over a plus h minus a, and that's how we just end up with that h in the denominator of the slope of this secant line connecting these 2 points. So the slope of the green line, which is connecting these 2 points, is given by this expression right here. And I'm being very careful what I'm circling there. So let me just say that one more time. The slope of the green line, which is the slope of the secant line, is what I've just put in parentheses there. And then sort of the whole magic of Calc 1 was to say, let's look at the limit as the distance between the two x-coordinates goes to 0. And that will give us, so once we take the limit, what I've got in the red brackets here is the slope of the tangent line to the curve that's formed. So it's not the slope of the, I want to be very careful here. I'm not talking about, there's no such thing as a slope of a tangent line. There's no tangent line to a surface. Okay? By the way, if you're curious, we will talk about a tangent plane to a surface in a couple of sections. There's no such thing as a tangent line to a surface, but if I intersect the surface with a plane, then I've got a curve, and I'm back to being able to talk about tangent lines. And that's what we see in this image here. Okay? By the way, we're going to give the slope of that line, we're going to denote it by either f sub x of AB. That's one way we're going to denote it. That's read the partial derivative of f with respect to x. Or we could denote it the way you've already seen it, where we'll write partial f partial x evaluated at the ordered pair AB. I'm going to write that slightly differently. Usually when we write it evaluated, we'd write like this, evaluated at the ordered pair AB. Okay, so I do want to stop now. I don't want to get too hypothetical about what's coming, because I am going to address that. But are there questions about this process right here? Any questions on the notation? Any questions on the idea of secant lines versus tangent lines? Does anyone want to ask anything now?
So the secant line is the line between A and A plus H.
Yes.
And a tangent line is just the line tangent to the curve at one point.
Great. Yeah, let's talk about that. That's exactly right, Xavier, and let's just do a quick recap of that. So in Calc 1, our general way, so our goal in Calc 1 was to come up with the slope of the tangent line, passing through the function at this point. Okay? So this would maybe be the order pair A, comma, f of A in Calc 1. Okay? Folks, before you got to calculus, how did you compute slopes of lines? You always found what? 2 points, and then you did the slope formula. You found the ratio of rise over run. Okay? What is hard about finding the slope of a tangent line? This is really important. Let's make sure we're all on the same page here. What's hard about finding the slope of a tangent line?
You have to use limits, because if you try to find the slope of a tangent line using the rise over run formula, your run is going to be 0, and you can't divide by 0.
That's a great way. That's a really good way to describe that, Dustin. Yeah, I'm gonna oversimplify it. Normally, when we go to find the slope of a line, we use 2 points. What's the problem here? All I know about this blue line here is 1 point, so I'm at a loss. So our strategy in Calc 1 was to take some other point on the curve and not compute the slope of the blue line. Oof, that's ugly. Not compute the slope of the blue line. But compute the slope of the secant line. This is a secant line connecting, and let's go ahead and label some things here. X equals A and x equals A plus H. Okay? So that black line there is called a secant line, and the blue line is the tangent line of f at x equals A. Okay? So the whole strategy for the first half of Calc 1 was to come up with the slope of a tangent line by taking successive approximations of the slope of the secant line. So you can see this black line, the slope of this black line is not the same as the slope of this blue line. They do not have the same slope. They're in the right ballpark though, right? They're both negative. Okay? But how do I get a better approximation of the slope of the black line? By bringing this x-coordinate closer to the original point, the original x value. That's going to have the effect of moving this point closer and closer, and if we recompute the slope of the secant line, it's going to be a better approximation for the slope of the tangent line. For that to happen, though, what has to happen? H has to go to 0, and that's how you got your limit definition of the derivative in Calc 1. Great. So back to this, what we basically do is we take a planar slice of our surface, not just any planar slice, although we'll do that in the next section, but one that is parallel to the x-axis, right? So we've got, in fact, let's just say this. We take a planar slice of the form y equals b, so it's passing through that ordered pair a comma b in a way that we now have this plane is perpendicular to the xz plane. Or excuse me, this plane is parallel to the xz plane. And now inside of this plane, we now have a Calc 1 problem of finding the slope of the tangent line for the curve that's formed by the intersection of the plane and the surface. Great. So then once we've got that, and once we've got a notion of limits, looks like my pictures got shifted here. That's pretty bad. Once we got the notion of limits, we can go ahead and give a way of finding the slope of the tangent line inside that plane. Okay? And we're going to call that the partial derivative of f with respect to x. So I guess we're done, right? So we take these 2 points here. So we're going to take 2 points inside this planar region. So let me zoom in on that a little bit more. Gosh, everything got shifted down here, folks. I apologize for that. I'm just going to kind of clean this up. Is that okay? You wouldn't mind if I clean that up? All right. So the slope of this line right here is simply f of a plus h comma b minus f of a comma b. So that's this z value minus this z value, right? We're doing a z2 minus z1 all over, and then we've got the, because we're restricting ourselves just to this plane here, we can think of that from the x value a plus h minus a. Okay? That's the slope of the secant line. We could simplify that, of course, so we've got f of a plus h comma b minus f of a b all over h. That's still the slope of the secant line, but as soon as I take the limit as h approaches 0, this is going to be the slope of that tangent line. And this is how we choose to define the partial derivative of f with respect to x at the ordered pair a comma b. So there's our definition of the partial derivative of f with respect to x at a given point.
That's the slope of the tangent line.
Well, yes, but let's just be a little bit careful there. It's the slope of this tangent line right here, yes, but I want to make sure that we're not talking about the slope. There's no such thing as the slope of a tangent line to a surface, right? There's the slope of the tangent line of the intersection of the surface and the plane y equals b. That, once we take the intersection of those two, gives us a curve, and yes, that is then the slope of the tangent line on that curve. But it's really important to me that when you say, is that the slope of the tangent line, that we're making sure we're restricting ourselves to that plane where y equals b. Great.
Wouldn't that always be undefined? Because h is approaching 0.
Oh no. If that were true too, all of calculus would be undefined, right? Because when you go ahead and say, for f of x equals x squared, give the limit definition of the derivative, that's the limit as h approaches 0 of f of x plus h minus f of x all over h? What a great question. Okay. Sure, I can't plug in a 0 for h there, right? But limits aren't plugging in numbers, right? Sometimes evaluating limits boils down to, once you've done some steps, direct substitution. I can't do direct substitution here, but in Calc 1, you learned how to do this with, you did the limit as h approaches 0 of x plus h quantity squared minus x squared all over h. And then you did some clever algebra tricks so you could eventually cancel out that factor of h. Then you could use direct substitution. So you're right. This expression inside my parentheses here is not defined at h equals 0. But when I take the limit as h approaches 0, I examine the behavior of those output values. And if they are approaching a number, then that indeed is the derivative, specifically the partial derivative of f with respect to x. Great question. Great question. Okay. Oh, another question.
Just getting rid of the limit makes it the slope of the secant line?
Correct.
Okay.
But you can't plug in 0 for h. H is representing the distance between those two, the distance between the x coordinates of those 2 points. Great. So we move along, and we can do the exact same thing here now. We're going to develop the exact same idea, but now we're going to take the same surface as before. We're going to take the same ordered pair in our domain, the same ordered pair a comma b. We're going to get then an ordered triplet, which gives us the point on this surface. Okay. But now what we want to do is we're interested in, as we move along the y direction, how does our z value change? How does z change as we move in the y direction? So what are we going to do? To be able to get some sort of meaningful interpretation of that, we're going to intersect that with the plane x equals a. It says, oh great, it says it right there. We're going to intersect this with the plane where x equals a. Now, when we look at the intersection of the plane x equals a and our surface, we've got a curve in the yz plane. Put another way, x doesn't really factor into this. Because another way to say it is, think of it as holding the x values constant. So even though x and y are both independent variables, let's hold one of them constant and look at how the other one changes. And how changes in that other variable, the non-fixed one, affect the outputs of the function. Great. Excuse me. All right. So we do the exact same thing here. We've now got these two coordinates. This is the coordinate a comma b plus h comma f of a comma b plus h. That's that ordered triplet. Okay. And then here was the original ordered triplet a comma b comma f of a b. And then we compute the slope of the secant line connecting those 2 points. And so the slope of the secant line connecting those 2 points would be the change. And so again, I want you to think about this as the slope formula here is sort of like z2 minus z1 all over y2 minus y1. Because we're in that yz plane now. Okay? That's kind of our impetus for going forward. And so the slope of that secant line would be f of a comma b plus h minus f of a comma b all over b plus h minus b, which I'll rewrite one more time as f of a comma b plus h minus f of a b all over h. This is still the slope of that secant line, as Xavier was saying before. That's the slope of the secant line. To make that approximate, so we're using the slope of the secant line as sort of a stand-in for the slope of the tangent line, but to make that approximation a better approximation, we look at the limit as h goes to 0. And this gives us the partial derivative of f. And let's see, we're using a capital, I guess we're using a lowercase f here. The partial derivative of f with respect to y at that ordered pair. Okay.
Question.
Yes, sir.
So, I think I didn't really understand what B is. For the previous one, A was like the x on the x-axis, the
Yep.
x coordinate, and B is the what?
The y coordinate.
Okay, so I think I'm getting confused. Like what's? Okay, no.
Yeah.
F of A B is the z coordinate.
Correct. Z is equal to, you get the third variable by plugging in the ordered pair a comma b. You get the third value.
So for the partial with respect to y, is A still the x?
Yes.
Like A is x.
Yes. So remember, these ordered triplets, Xavier, are not just a triplet, they're an ordered triplet. So whatever coordinate comes first is understood to be the x coordinate.
Okay then, so what's the difference between the partial with respect to y and the partial with respect to x if it's literally the same equation?
But it's not. Where's the plus h in this problem? It's with the b, right? The y coordinate. So one way to look at this, Xavier, is we are fixing the x coordinate and changing the y coordinate slightly, and then asking the question, what's the overall effect to our function if we fix the x coordinate and just nudge the y coordinate slightly? Go back and look at the definition here for the partial with respect to x. Here we fixed the b coordinate. That did not change. And we nudged the x coordinate slightly. And then we ask, how does that affect the output of the function? Yeah, great question.
Gotcha.
Great question.
Thank you.
Yeah. Okay, folks. One of the things that's going to be a little bit daunting at first, but I promise after a day you're going to feel real comfortable with it, is some of our notation for partial derivatives. Okay. I'm going to keep building onto this as we do as we add in our second derivatives, which are interesting. Our second partials they're called, and some of them are mixed, and there's a lot of stuff going on. So I'm going to add to this, but let's just clear this up. The partial derivative with respect to x at a point is denoted, one way to denote it is this way. That's the partial derivative of the function with respect to the variable x at the coordinates at the point AB. And that's what we've been looking at before, right? That's what we were just looking at, was saying pick a point, nudge it slightly in the x direction, and look how the y coordinates change. But just like you saw in Calc 1, right, if you remember, and one thing I would highly encourage you to do is go back and look at the first few sections of calculus in this book. One of the things we did in Calc 1 was first we defined the derivative at a point, meaning we found the slope of the tangent line at a point on a curve. But then we quickly moved on to, instead of thinking about just the derivative at a point, we thought of the derivative as a function in its own right. Right? And I think you guys are all very comfortable with saying, here's f of x equals x squared. You guys know the difference between f prime of x and f prime of 2. Right? That's the slope of the tangent line as a that's the slope of the tangent line at x equals 2 here. This is a function that outputs the slope of the tangent line. Okay? So I'm doing the same thing here. So another way, if I want to talk about the partial derivative of f with respect to the variable x as a function, that's how we denote it. Okay? That's one of the two notations that we commonly use, although there are many others. Okay? Another notation that we could use is this partial notation, where we would say the partial derivative of f with respect to x evaluated at the ordered pair a comma b. So this is the same notation here. By the way, folks, I'm probably still writing a little too big on this. So maybe write that a little bit smaller than I am. I'm sorry about that. So if I think about the partial derivative of f with respect to x as a function, I would just write it this way. That's one way to do it. Another way to do it is to say that's the partial with respect to x of f of xy. So what I'm talking about here, folks, in this expression right here, is sort of in one variable calculus we would have df dx. That represents the derivative as a function. Or we could also write it as ddx of f of x, which here we think of it as sort of saying take the first derivative of the function. Okay, so we're going to add to that. I guess we could quickly put in for y. For y, we would say f's of y of ab. Oof. Or we could also do partial f, partial y, evaluated at the order pair ab. That's if we're thinking of the partial derivative of f with respect to y at a point. That is, go to a point on the surface, move in the y direction, move in the positive y direction, and answer the question, how does your elevation change as you do that? So another way to denote that would be then, if we're thinking about the partial derivative of y as a function, we would denote it that way. Or partial f, partial y, that's a function. Or partial y of f of xy. So we're going to add to that. You should have a little bit of room left. We're going to add to that when we start looking at our second derivatives, which is where the notation can sometimes get intimidating. But after we go through it slowly, I think it'll clarify it. Okay. All right, the next thing I want to do is let's actually compute some partial derivatives as functions. Notice here I'm not talking about finding... this is not saying go to the order pair AB, take a slice along parallel to the x-axis, take a planar slice parallel to the x-axis, and then ask the question, what's the slope of the tangent line at that point? That's what we just did. Now I'm saying, let's think of the partial derivative of f with respect to x as its own function. Let's go find that function. We're going to do this twice through this long way, and then say never again, because we'll see the pattern. We'll see what happens here, and then we'll be able to start taking derivatives lickety-split, sort of the way in Calc 1 you first did limit definitions, then you learned rules to shortcut those definitions. All right, so here this is the long way, and I wouldn't put it past me to ask a limit definition on your next test. I might not. If I do, it won't be an exceptionally tedious one. It's just to see if you can handle this, okay? All right, so we would say that partial f, partial x, by definition, is equal to the limit as h approaches 0 of f of x plus h comma y minus f of x comma y all over h. Okay? And I'm going to work through this one, but off to the side here, what I'd like you to do is I'd like you to go ahead and answer this question. What's the limit definition of partial f, partial y? Follow your nose and do that right-hand side. So this is going to be the limit as h approaches 0. That part looks the same. I'm still going to have an all over h, right? That part's not going to change. What's the difference here, folks? The difference here is I want you to think of, we're going to fix the x variable. We're not going to allow the x variable to change. We're not going to nudge that. And we're only going to nudge the y variable. So we've got f of x comma y plus h minus f of xy. Does anyone have any questions? Because if you've got questions here, at this point, I'm not doing my job, and I got to clarify it. Okay, we keep moving. So I'm going to go ahead and finish this limit out. Let's see here. Yeah, thanks for the feedback, folks. I always appreciate a thumbs up or something like that. Or, let's see here. You guys had that whole array of emotion. You've got a crying one. Does everyone see my picture? It's the computer one. The picture crying. That could mean help, or this, that looks like I need help. Okay, so feel free to use that. If you're feeling good though, when I ask you, hey, how we doing? Yeah, you've got the thumbs up, you got the clap, you got the party streamers. Okay, so please, that feedback does really, really help me as I'm talking with you. Okay. All right, so here we go. We've got the limit now as h approaches 0 of x plus h quantity squared y minus x squared y all over h. Any questions about that second step, folks? How we give me a feedback. Give me a thumbs up or a crying face. Awesome. Getting some feedback. Xavier, you got a question on that?
Yeah, I'm probably just thinking too slowly.
So, if I say, if I said here f of xy is x squared y, and I say find.
I get it.
Oh, you got it?
Yeah, I just thought slowly. Sorry.
Okay, no worries, no worries. That's why we're doing this. Okay, please, folks, you paid good money to be in class today, so when you have questions, ask them.
I have a question.
Yeah, I'm sorry. Who's asking? I don't see who's asking.
Phoebe.
Phoebe. Oh yeah, go ahead.
So we're finding the secant line or tangent line that is from a slice taken parallel to the z-axis and also usually to like the y or x-axis. What if you had a slice that is still parallel to the z-axis but goes through the x and y? So it's like
an oblique one at an angle.
Can you find the secant line along that slice?
Yeah, that's it. No, it actually makes perfect sense. I'm just going to talk about it real briefly. We're going to move on in a little bit, and we're going to say, hey, what if we took? So we'll do this in a couple sections. What if we took a planar slice that's not parallel to either of those two axes? And then we'll ask the question: as I move in that direction, how does my elevation change? That's a perfectly fair question. That's a question for what's called the directional derivative. So again, I've said that there's many different derivatives we're going to be developing in Calc 3. That's a question for what's called the directional derivative, and that's a couple days down, or I think that's tomorrow. I can't remember exactly when it is. I'm kind of, yeah, great question. Okay, so folks, here we've got the limit as h approaches 0 of, well, actually, let me do this now. Notice that both terms in the numerator have a common factor of h. I'll be a little pedantic today because this is our first time doing it. We may be a little rusty with this. So let me pull out the h from inside that fraction. And by the way, that gives me x squared.
Y, right? Pull out the y. Yeah.
Oh, yeah. Thank you. It gives me x squared plus 2x plus 2xh plus h squared minus x squared all over h. So I did two things at once, folks. I factored a y out of the fraction, but for right now I left it in the limit, although you could have done this in one step here. I factored a y out of the fraction, and I also expanded the x plus h quantity squared. That part should seem very reminiscent of Calc 1. Okay, but here's where we got to start. I mean, it's multivariate calculus, folks. We've got lots of variables. Y does not change as h changes. So as far as y is concerned, as far as h is concerned, y is a constant. And what can I do with constants in regards to limits?
You can pull them out of it.
Bingo. Exactly, Aya. So we got the limit as h approaches 0 of, and notice inside here, my x squareds cancel. That should seem reminiscent of Calc 1. And I'm left with y is equal to, I've left with that is equal to the limit. As h approaches 0, I can factor out an h. I'm not going to do the work to do that. I'll just jump to the result. That's 2x plus 1. 2x plus h. And now I can evaluate this new limit. So, Aya, you asked a great question before. I could not evaluate this limit through direct substitution because of that factor of h in the denominator. But by the time I get down to here, this new expression, which is equivalent to the old expression everywhere except for at h, can be evaluated through direct substitution, and so we do so. So we get 2x plus 0, and so we get 2xy is the partial derivative of f with respect to x. Okay. I'm going to do this second part again. I'm going to do it fairly quickly here, folks. So that's the limit as h approaches 0 of, and now I'm going to have, this is the critical step, so we'll slow down for this one, x squared times y plus h minus x squared y all over h. Okay, so like Xavier said, this takes a minute to digest. Take a second, look at that, see what I did there. I took the function x squared comma y, and I left the x alone, but I replaced the y variable with y plus h in this first expression here. So there's the y plus h. There it is again in place of the variable y in our original function. How we doing, folks? Thank you. Appreciate the feedback. Great. So now, just like before, and I'm going to do this part a lot faster now. That's the limit as h approaches 0 of y plus h minus y all over h. Bibbidi bobbidi, we get then just the limit as h approaches 0 of the constant 1, which is just x squared. Now, before we say the obvious, I want to see if there's any questions about the limit procedure. Don't ask if there's another way to do this. There is, but I want to make sure you understand the limit procedure. One of the key steps, folks, was that notice that because I kept the x constant, I had the same x expression, looking at this first problem here, because I kept the y constant, I had the same y factor in the numerator. That will always be the case. If y is being constant, the same y components will show up in both terms in the numerator, which means what? You will always be able to factor out the y components when you're taking the partial derivative with respect to x. Likewise, if these two expressions are identical as far as x is concerned, they're going to have the same x expressions in the limit. I'll always be able to factor that x expression out. And then look what I'm doing. At that point, I'm just taking the Calc 1 derivative of y. Or over here, I'm taking the Calc 1 derivative of x. That is, let's look at the original problem. Where is it? F of xy is equal to x squared y. Folks, how do I calculate partial f, partial x? I treat y as a constant and take x's derivative. How do I take partial f, partial y? I take y's derivative, holding x as if it were a constant. What's the derivative of a constant times y? It's just that constant. As far as computing partial derivatives go, there is no real difference between doing a derivative in Calc 1 and a derivative in Calc 3, you just remember, hey, if I'm taking the derivative with respect to y, I treat x as a constant. Any questions on that, folks? I need to make sure you see this. So if you're feeling lost right now, don't worry, it'll be clear as day in a moment, but I need to make sure, I need to know whether you have a question, because that lets me figure out what I need to say to nudge you over to seeing it. Thank you. Give me thumbs up, thumbs down, or thumbs up or crying face, one or the other. I'm getting some thumbs ups. Dennis, how are we doing today?
I'm excellent, sir. How are you?
Good. You doing well?
Oh, yeah.
Great. Zachary, how are we doing? Or Zach, how are we doing today? Great. Okay. I think that's everybody. All right. So let's actually do some more interesting, or let's do this a little bit faster now. Okay. So we've got f of x comma y is equal to, I'm sorry, I don't know why I'm rewriting it. It's just a habit. All right. Let's go ahead and calculate partial of f with respect to x. And so what am I going to do? I'm going to take the derivative of this function with respect to x, treating y as a constant. And here we go. We get 3x squared plus 4y. I treated the y as if it were just the letter A or the letter B. Okay? So let's have you guys all do the partial derivative with respect to y. I should have put the... it would have been polite to put the xy there. You don't have to, folks. Notice I didn't put it here, but it's usually polite to give the, of xy. Everyone take the partial derivative of f with respect to y. Minus 6y plus 4x. Thank you. Appreciate that. Nice. Great. Okay, folks. Partial derivatives are kind of fun. They're like I don't know, they're like a pleasing exercise. I don't know, like doing crosswords or word searches or something like that. Okay? Maybe not crosswords. Crosswords can be tough. They're like doing a word find, right? They're a nice little exercise. Okay?
But you're just saying that this is easier than a crossword, then?
I think you'll find that in a moment. And maybe not right now. Now, we're going to keep building on this. So as is, I hate to say it, but whenever something goes kind of smoothly in a math class, what do we do right after it? We make it harder.
I have a question.
Yeah, go ahead, Allison. Yeah, or whoever that was.
I know that the negative 3y squared, we're treating that... What?
Yep, you're exactly right.
And
So
x cubed, I know we're treating that as a constant, but we don't include it in the final answer.
that's correct. I mean, what you could do, if you wanted to, Allison, you could write 0 minus... So 0 minus...
Oh, and the other one, with respect to x. I'm confused on that one.
Okay, yeah, so let me report what I had here. We had minus 6y plus 4x. So this term right here was constant. So if you like, what you could have done was you could have said that's plus 0 plus 4y. Does that make sense?
Oh, well, yeah.
Okay, so Allison, let's think of it like this. If I gave you just this other function, g of x was equal to 4x times a, and I said, what's the derivative? You would say the derivative is 4a. Do you agree?
Yeah.
So in our problem here,
Yeah.
Sorry. In our problem here, maybe we have h of x is equal to 4xy, then same thing. That derivative would be 4y. Where we're thinking of, because here I've said, now this is literally how you would do the derivative. Notice this is a traditional, notice I'm using the prime notation from Calc 1, because I am saying this function only depends on x. Even though I've written the letter y there, I'm treating y as a constant. Y is usually used for a variable, but in this problem I'm treating it as a constant. Now, the difference is that over here, when I look at, say, k of xy, equals 4xy. The difference here is I am treating y is a variable, so when I go to take the derivative, I have to use the partial notation to denote that this is a multivariate function, but then the act of taking the derivative is to hold y as if it were constant. And so we get the same answer that we got over here. The difference is that's a Calc 1 problem because this function only depended on x, so even though y looks like a variable, it is a constant. Over here, y is a variable, but we treat it like a constant when taking the derivative.
That makes sense.
Great, great. Okay, folks.
Thank you.
Yeah, let's keep going. Here we go. Let's just do some more interesting problems. So we've got partial f, partial x is equal to, and I'm just going to run through this. I'm going to treat y as a constant. So the derivative of this would be y cosine xy plus, here I've got to do a product rule, so x squared times y e to the xy plus 2x e to the xy, applying the product rule there. I did that really fast. I should have let you guys have some time to think about it. Yeah, I appreciate that. Yeah, go ahead and just take your time. Give me a thumbs up when you feel good about it. If you don't, please immediately tell me. I'm not sure what you did there. Thank you, folks. Take your time. There's no rush here. I did that way too fast. I'm jazzed on coffee right now, so. Okay, I'd like to move on, but let me see if there's questions. I haven't seen anybody appear to ask a question, but if you have a question, now would be a great time to do so. Yes, yeah, let me go ahead and look at that. So, in this first problem, this is like if I said, hey folks, I've got the sine of ax, what's its derivative? And so its derivative would be, well, the derivative of the sine of something is the cosine of that something, right? But then by the chain rule, I would have to multiply by the derivative of what was inside there, and the derivative of ax would be a. So you see that's precisely what I have here, except I've got the letter y instead of a. Now, for here, as far as x is concerned, I've got a product of two functions. So I had to do my product rule from Calc 1. Here is the first, and I didn't say this, and so this would be a great question to ask. Does the product rule carry over for multivariate calculus? And the answer is yes. Okay. So here's the first times the derivative of the second, plus the derivative of the first times the second. But again, I'm treating this as if let's say I gave you the function f of x is equal to x squared e to the 3xy, 3 to e to the 3x. So in place of that 3 there, I've just got a y. So there's the first term, and then what's the derivative of e to the 3y? It would be 3e to the 3y, right? Or excuse me, doggone it. What's the derivative of e to the 3x? It would be 3e to the 3x, right? And that's what I've put here, just a y instead of a 3. Any questions?
So we can consider the variable we're keeping constant is just like an a.
Exactly. That's what it means to keep it constant. Yeah. So, or even if you want to be even more explicit, you could think of it as a 3 for the time being. But make sure you replace it with a y when you're done. Yeah. Great. Are there questions on that? Okay, I'm going to go ahead and move on.
Are we ever going to have... I see that we're just doing like regular partials now. Are we going to have to use what you just taught us, like the partial, the limits?
Yes. I have not ruled out that possibility, that I could ask you to do a limit definition. I'm not going to do a hard one because you did all the, because basically these are the same problems as Calc 1. The only real difference is, when we did the limit definition, is to actually give the correct definition. That's the part that looks different than Calc 1. All the rest of the work is the same as Calc 1. So I'm not going to ask you a hard problem with this, but it's possible that I ask you to use the limit definition. And on the MyMathLab, if you're asked to use the limit definition on the MyMathLab, do make sure you do that. Okay? I'm not going to do any crazy ones that require multiplying by conjugates or some complicated techniques. They're always going to be just this real simple factoring out, eventually cancel out the h and move on. Yeah, great question.
When we use the limit definition for 15.2 problems, where I was asking like the limit.
Well, let's be careful here. So limits are a topic in their own right.
Mhm.
And then the limit of the slope of a secant line
Oh yeah.
is the derivative. So that's a very special type of limit. Yeah. Hosanna asked a question. So just to confirm, great question. Integration by parts, I don't see what that next, NVM, what does that mean? I'm sorry.
That's not mine.
Never mind.
Mine, yeah. I wrote derivative, but then I remembered it's integration.
Yeah. So in a way that's true, because we can talk about finding antiderivatives, but we don't really know what that means yet. So not quite. But in a sense that like the mechanics will be, I think we can do something like integration by parts in these problems, but we don't know what it means to integrate. Yeah, great question. Sorry, folks, I don't know my three-letter acronyms. I'm just not cool. All right. Let's see here. Where are we? Yeah. All right, let's go ahead and we're just going to do the first one here, folks. I'm going to go ahead and evaluate this one. So if we compute partial f partial x as a function, that would be, this one's not very fun. That would be 1 over y, right? So put another way, if you had trouble with that, rewrite the function as f of xy equals 1 over y times x. What's the derivative of x? It would just be its slope. Okay. And so then we would say that the derivative of f with respect to x evaluated at the ordered pair 1, 2 is what? Well, I'm going to replace all of the x's in this expression with a 1. And I'm going to replace all the y's in this expression, I made that so big, with a 2. I guess this isn't bad. Let's finish it up. Partial f partial y would be minus x over y squared. It's just the Calc 1 problem, treating that x as a constant. Okay. Again, if you're rusty on Calc 1, you would rewrite f of x, y. Most people in Calc 1 would rewrite it this way, y to the minus 1 power. Then when we take partial f partial x, they would say, that's minus 1x y to the minus 2, and then they would just rewrite it this way. So then we're going to evaluate that. Okay, interpret this for me, folks. What we're saying is, let's go ahead and finish it out. Let's go 1, 2, so that'd be negative 1 over 2 squared, which is negative 1/4. Okay. So I'd like to interpret this real quick. I'm going to make this surface up. This is not going to be what this surface really is. I want you to just imagine this is my surface here. There's my surface. Z is equal to f of x, y. So, for instance, let's see here. Hopefully this will work out okay. Yeah, at the point, what's my point here, folks? What's my ordered triplet? It would be the ordered pair, or the ordered triplet 1, 2, 1/2. Does everyone see where I got the 1/2 from? That's f of 1 comma 2, which would be 1 over 2, which is 1/2. That's the point on the curve, right? So this first bit of information tells me that so here's my x-axis, here's my y-axis. If I move in the positive x direction, approximately for every 1 unit I move in the x direction, I'm going to go up 1/2 unit in the z direction. You can see my picture's not true to life there. Does that make sense?
Can you repeat that one more time?
Yes. So we found that the partial of f with respect to x evaluated at the ordered pair 1 comma 2 was 1/2. That means if I go to that point on the function, that red point right there, and then I step along in the positive x direction, my y value should be rising at a rate of about 1/2 for every 1 unit I go over. So for example, I would expect this point right here to be, it'd be 1 plus a little bit, comma 2, comma 1/2 plus a little bit. A different little bit. But that's a positive increase as I scoot it over. That's only as I go along the x direction there. Okay. So in fact, we'll just fake it. Let me put the curve like that. Now it looks like as I'm stepping in the positive x direction, what are my y values doing? They're increasing.
So I have a question.
Uh-huh.
Z is f of x, y.
Yep.
So is it 1/2 in respect to the original function?
That's
or with
for the
partial derivative.
Great question. This was not a great example to draw a picture for. This 1/2 is because f of 1 comma 2 is 1/2. If I could...
I don't know which one to use. Like, partial derivative with respect to y or with respect to x.
Well, neither right now. If you're looking for the if you're looking for the z value on a function, you don't plug it into a derivative, right? If I'm just saying where is the z coordinate at, you're going to plug your order pairs into the original function. Yeah. So what I'm saying here is if you put a slope on this tangent line right here, the slope, and I can't draw in 3 dimensions, folks, the slope of that tangent line is a positive 1/2. That 1/2 corresponds to that 1/2. So there's 2 1/2s right now, and I'm sorry for that.
That makes more sense.
Great, great. And then we're saying that if I go along the positive y direction, and again, this picture's getting cluttered, but if I go along the positive y direction and I compute the slope of the tangent line there, the slope of the tangent line right there would be negative 1/4. Meaning, go to the ordered triplet, 1 comma 2 comma 1/2, step a little bit in the y direction, the positive y direction, and you're going to be going downhill at a rate of negative 1/4. Great questions, folks.
Can you find the rate of change in the negative y direction?
Yes, but the partial derivative function doesn't do that for us. Now, you could say, now, careful here. We could immediately say, if you were to step in the other direction, if you're stepping the negative y direction, you would expect to be rising at a rate of 1/4 as you go in the negative y direction. You could say that, but what you're actually getting into is the topic of a directional derivative saying, hey, start at a point, move in any direction, what's going to happen? Right now, in this section, we're just saying, go to a point, leave your y direction alone, step in the x, what's going to happen? Go to a point, leave the x direction alone, step in the y direction, what's going to happen? That's all we're answering today. So I don't, I mean, although you could answer that, I'd rather save that for the directional derivative topic. Yeah.
Is there a slope in the z direction we need to know?
No.
Okay.
Yeah, that's because Xavier, z is a function. So what we're asking when we say for a derivative is, if I adjust the independent variable, how does the dependent variable change? And z is our dependent variable here, so it doesn't make sense to ask the other way around. Now, if I have a function of higher variables, like I do right here, now it does make sense to say what is partial f partial z. But we can't picture this function. Why? Because this function requires an ordered triplet as an input, and it lives where? In 4 dimensions. Oh, I've got quite a delay there, folks, on my video. Sorry about that. Okay, I've got that we're a ways in, so I'd like to go ahead and pause here, and we'll start back up at 25, please. All right, I'm recording. We're back. I didn't give a definition for what it means to take the partial derivative of a function of 3 variables with respect to the third variable z, but I think you could probably guess what it is. And so rather than actually giving it as a definition, we're just jumping right into it. Here we go. So partial f, so in fact we're using this other notation here, f sub x would be 4xy minus 6xz to the fourth. And I'm going to go ahead and just emphasize by putting a plus 0 there, because when I take the partial derivative of that last term with respect to the variable x, it's being treated as a constant, and that derivative of that constant is 0. So when I take the partial derivative with respect to y, we get 2x squared. I'm going to put plus 0 for that middle term, and then we get plus 20yz squared. And so here's the new one. Nothing really exciting, though, by jumping up another dimension. We get f of z would be 0 minus 12x squared z cubed plus 20y squared z. I think, as long as I didn't make a mistake. Any questions on that, folks? All right, let's extend it.
I'm sorry, I do have a question really fast.
Yeah, go ahead.
With respect to z,
Yep.
on the very last term where it says 20y squared z.
Uh-huh.
Oh, never mind, I get it. I'm sorry.
That's all right. That's all right. It's worth checking. Please, folks, it's you know, a lot of these things become second nature very quickly, but you know, for some of us it takes half an hour to become second nature, and for some of us it takes an hour to become second nature. So take your time. Feel free to keep asking questions. Okay? This is tough. I thought this was a fun problem. I'm sorry. I like the fundamental theorem of calculus a whole lot, so I always find those questions enjoyable. So we'll take partial f, partial x. That's equal to partial x of the integral of xy h of s ds. Then what I'm going to do here, so folks, don't let your eyes glaze over. This is just saying take the partial derivative with respect to x, but I'd like to use the fundamental theorem of calculus part 1. And for me to do that, remember that said that the derivative with respect to x of a to the x of f of tau d tau, that's where we use that dummy variable. In this case, we're using the dummy variable s. By the fundamental theorem of calculus, what does it mean to take the derivative of this integral? It means just to evaluate the function at that x coordinate. This is Calc 1. So if you're rusty on that, you're going to have a hard time with this problem. So if you're rusty on this, go back and review it first and then return to this problem. Okay, what I need to do in order to use the fundamental theorem is I need to change the sign on this integral and rewrite it as y to x of h of s ds. And then by the fundamental theorem of calculus, that's just minus h of x. If you want to find partial f, partial y, you would just get h of y. Okay. Folks, if I lost you on that question, I'm not concerned. Okay? I'm not concerned. That's a fundamental theorem of calculus question. I would love to talk about it during office hours some other time. I'm not going to test you on it. But math people love, you go on to another math course, they love to give you an expression like this because it looks intimidating as all get out. But there's no work involved. It's just application of a theorem. All right. All right, now let's move on to our notation here. So what I'd like to do is go talk about, before we do number 11, I'd like to scroll back up to where we were listing our notations. And I'd like to talk about the second derivative notations. Now, in Calc 1, we only integrated with respect to one variable, and so there was only one second derivative. Sorry, I said integrated. We only differentiated with respect to one variable, and so there was only one second derivative. We've already got two first derivatives, in a sense, two partial first derivatives, and so then we can take the partial of each of those with respect to either variable, and so there are actually a total of 4 different second partial derivatives. Okay? So for example, I could find I'm not going to worry about doing the points anymore. I'm just going to do the second derivative notation. So let's do that second D notation. So this says take the second derivative of x with respect to, take the second derivative of f with respect to x both times. Okay? Another way I could write that is to say that's partial squared f partial x squared. Okay. Now, neither of these really explains what's going on, so let's step into this notation here where I say that's partial x of partial f partial x. This should be the clarifying statement. And if it's not, that's okay, we'll get it fixed. Okay? But that's the one that clarifies what we're doing. This says take the partial with respect to x, then take the partial of the result, also with respect to x. Now, folks, this is definitely going to be one of those scenarios where I've used this notation for 20 years. And so I'm very comfortable with it, but I could see that the first time you learn this is pretty complicated looking notation. Okay? This fits with what you did in Calc 1. If you remember here, if we had f of x was equal to, let's say, x cubed, in Calc 1, we could represent the derivative this way. That's 3x squared. And then the second derivative we could do this way, right, which would be 6x. But we could also use Leibniz notation. And so when I took the first derivative, I wrote this. And then when I took the second derivative, this is how you write it in Leibniz notation. And most of the time, you guys just sort of didn't even think about what was in that denominator there. Which it didn't matter, right? Because we were taking we only had one variable to take it with respect to. But this meant to take the derivative with respect to x of the first derivative. Take the derivative of the derivative. Which would be to take the derivative with respect to x of your previous answer, which is how we get 6x. Okay? That's exactly what I did over here. So let's practice reading this together. This says taking the second partial derivative of f with respect to x both times. Okay? So I'll go ahead and put up fyy there, but I don't think there's any surprises in this one. There's no way you could go wrong with this one. But then we have what are called our mixed partials. And that's where I'm going to take, now here I've got to be very careful. Watch the change in notation here, folks. This is really important. And it's easy to get confused. So after I get done, we'll kind of all agree on something, or you guys won't have a choice, but we'll pretend we're agreeing. And so I'm going to have f sub x, y, and that's equal to partial squared f, partial x, partial y. And I don't know if I read that in the right direction, but that's how you write it. And here the order does matter for a moment.
What did you say those were called?
Those are called, we call these the mixed partials.
Okay.
And you can see that, so it's a second partial, but it's we're mixing what we're taking the derivative with respect to. Yeah. And so let me rewrite this one more time. That's the same thing as the partial with respect to y of the partial of f with respect to x. So everyone, this one should clarify what order you do things in. You take your function, you take the partial derivative of that with respect to x, and you get a result. And then you take the partial derivative of that result, but with respect to y. Okay? The one thing that's problematic is that these two different types of notations write them in a different order. So, how do you remember the order? With our derivative notation, the way we do it is we think of what is closest to our function. And if you think of it that way, it explains the order in both ways we can represent it. Closest to the function here is the partial with respect to x. So I'm going to take the partial with respect to x first, and then the partial with respect to y. Okay? So again, I feel like this clarifies everything, but you'll see both of these notations as well. So if you think about what's closest to f, it explains which one you do first. So notice which is closer to f in this representation of the mixed partial, this first mixed partial. X is, so that says you take the partial with respect to x first, then the partial with respect to y. Kind of starting, just like order of operations, folks, working inside, then out. Same thing here. We're going to start inside, meaning with the x first, and that one's a little bit harder to see, but that's the closest one, and then y. And again, this example should clarify this notational use. So, and I'm a little out of room here, so I'm going to write it over here. I've got partial f y x. So that's equal to partial squared f all over, and then I want you guys to write the denominator before I write it. So that denominator, we're going to take the partial with respect to y and then the partial with respect to x. Okay? So this ordering says do the y first and then the x. Likewise, this says do the y first, then the x. But do you see the difference? We're reading one left to right and the other right to left. But it makes sense if you think of it as right. In both cases, we're reading it inside out. So here's the clarifying way to represent it. That's partial x of partial f partial y. So here, first you take the derivative with respect to y, and then you take the result of that with respect to x. All right, that's all very abstract. Let's do some examples. Let's clarify that. So, I asked you to find all second partial derivatives here. How many are we looking for, folks? 4 of them. So, you just sort of, everyone comes up with their own systematic way of doing this. I'm going to first find partial f partial x. And that gives me 12x cubed y minus 2 y plus 5y cubed. Then I'm going to go ahead and find partial squared f partial x squared. So what do I do, folks, to find this derivative? If you feel like you really got it, please hold off on answering. I kind of want to make sure everyone's clear. So only answer if you don't know the answer. That's what I'm saying. We're taking the second partial of f with respect to x both times. So what am I going to do, folks? I'm going to take the answer from up here. What am I going to do? Think about it for a second. Go ahead.
Partial derivative of the previous result.
With respect to whom, Stephen?
X.
With respect to x. Okay. So I'm going to take this result, take the derivative again with respect to x. So this is going to give me 36 x squared y. And notice that the other two terms have no x's in them. And so that's the second partial. That's the second partial with respect to x both times. Okay? But also from this first partial, I can also go calculate partial squared f what? What's the order, folks? I've already done partial x, but I could take the partial of that with respect to y. And when I do so, we get 12x cubed minus 2 plus 15y squared. Okay. We found 2 of our 4 second partials. Okay, so what should I do now, folks? What should I do now?
Take the partial derivative with respect to y.
Of the original function, exactly. And when I do so, I'm going to get 3x to the 4th minus 2x plus 15xy squared. How are we doing, folks? Okay, so now let's go ahead and take what? Well, I think the easiest one to, well, it doesn't matter. We're going to take the second partial, and then we're going to take it with respect to y again. By the way, I notice I could write it that way, right, folks? I guess that's how I've been writing. I could write it that way, or else I could also write partial y, partial y. That's the same thing, right? Okay. So I'm going to take the second partial derivative of this first partial, okay, or I'm going to take the derivative of this first partial with respect to y again. Notice that the first 2 terms die off, and I'm left with 30xy. So I'd like everyone to write out the derivative expression before you actually take the next partial. Write it out as a derivative expression, just like we did over here and over here and over here. Write it out for the last one. Make sure you get the right one, and then compute it. That's silly. And there's our fourth second partial. Questions on that, folks? Thank you. Thanks for the feedback. Questions on that, folks?
I have a question slash comment. I don't really know.
Okay.
So it's just a coincidence that d squared f with respect to, you know, that, okay, so the fourth one we did.
Let's say it like this. The mixed partials. The two mixed partials.
Yeah, so the mixed partial where it's, you take it with respect to y first and then
With respect to x versus taking with respect
x versus x and then y. It's just a coincidence that they're the same in this case? Or is,
What a great question. Is it always going to be true? Is it sometimes going to be true? Or is this just like a one-off example? Let's hold off. Let's keep doing some more work. Okay.
I also had a quick question about the notation.
Yeah.
So in calculus, when we did like derivatives with respect to x, or just like the only variable, we also did the notation of d divided by dx. So we kind of excluded the f. So it wouldn't be df dx. Is that not a full statement if you don't include?
Yeah, great question. Yeah, Dennis, this is not the derivative of anything. This is what we call a derivative operator.
Okay.
You do it to something. Just like this on its own doesn't mean anything, but you take the square root of a number.
Right, okay.
So that notation on its own doesn't mean anything, but we would then apply it to a function f of x like that. Or we might apply it to, you know, the square root of x.
Okay.
So that is, so just the same way, when I wrote partial squared f, partial x, partial y, inside of there I've got partial x, partial f, partial y, and you could even take it one step further. You could write it, if you chose, partial x, partial y of f of x, y. I will often do this because I think this clarifies the order. I don't think this really clarifies a whole lot to take it one step further, but you could.
Okay, thank you.
Great questions, folks. Okay, in light of Dustin's question, let's keep going, and that looks like a typo to me, so let's change that to a y so we actually have something interesting to do. Okay. And so I'm going to go ahead and compute, we're going to kind of fly through this, folks, because I need to get to some other examples. So I'm going to compute f's of x, and that would be 2x sine of y. Then I'm going to go ahead and compute f's of xx, and so that would be 2 sine of y. Then I'm going to compute f of which one, folks? I've already taken the partial with respect to x, so this is what I want to highlight. What order do I do this in? Which one comes first? I've already taken the partial with respect to x. I'm doing one of my mixed partials.
so it should be f sub x sub y.
F sub xy, right? Because remember, we read inside out. And when we're doing this other notation, we first took the partial with respect to x, we're going to take the partial of that with respect to y. When we do that, we get 2x cosine y. Okay, folks, finish these out. Do the so you got to take partial f, partial y, and then find the other two second partials. Finish that out.
So when you ask us to give all second partial derivatives,
Yeah.
we have to do it in this specific order: f of x, f of x.
No.
No.
But you do need some sort of systematic way, Xavier. I would encourage you to have a system, because if I had you find third partials, you'd have to find, I think, 9 different third partial derivatives if it was a function of 3 variables, and it could get extremely complicated. So you want to have a system. I don't care what your system is, though. Yeah, that's up to you. Uh-oh. Is the world broken?
Yeah, I think you took it from the other second partial.
Oh, thank you, thank you. So let's go ahead and answer Dustin's question, because you learn to always do these mental checks. Dustin asked the question about the mixed partials. I was going a little fast there, and things weren't working out the way I expected them to. In this case, again, we had that the mixed partials for the second derivative equaled each other for a function of 2 variables. So there it is, twice in a row, where our mixed partials have given the same result. Is that always the case?
I mean, I think so. We did it twice. That's basically mathematical proof, right?
Yeah. This is one of the things I find most interesting, folks, because I've gone through the proof of Claro's theorem a couple times, and each time I say, okay, I get it. But it still amazes me every time this happens. I'm still always amazed by it. Okay? And Claro's theorem says that most of the time that's true. Now, it's actually not always true. Your mixed partials will not always be the same. But if your first partials, if those mixed partials are continuous functions, then they will always be the same. If those mixed partials come out to be continuous, then they will always agree with each other. They don't have to come out to be continuous. Folks, keep in mind the classic Calc 1 example. F of x is equal to the cube root of x. This function, let's do another one. Let's do x to the 4/3 power. Okay? This function, nice continuous function, defined everywhere. We take its first derivative. Okay. That will give me 4/3 x to the 1/3. Nice continuous function. Nice continuous function. But when I go to take the second derivative here, we get 4/9 x to the minus 2/3, which is 4/9 x to the 2/3. This function is defined at 0. This function is defined at 0. This second derivative does not exist at 0, so it's not continuous there. So a function like that, if that somehow showed up in your mixed partials, that would be a situation where the mixed partials may not agree with each other, because this function is not continuous around 0. So that's a place where Claro's theorem would break down. I'm not going to, you could find an example, dig up like clarifying examples to Claro's theorem or something like that on the internet, and that'll help you. I'm not going to worry about that, but I do want to say that it is not always the case, but it is the case that the mixed partials will agree if you're dealing with if those mixed partials are continuous, then they will agree with each other. Okay? So folks, just be careful. This does extend to higher variables, but it has to do with not all mixed partials, right? This mixed partial and this mixed partial there's nothing that says they're going to be the same. But notice that this has two x's and a z, this has two x's and a z, this has two x's and a z. So Claro's theorem, that's the extension to Claro's theorem. I don't want to worry about that. That's as far as I'm going to go with it. Take care, sir. I think you left. Okay, great. Okay. We're going to hold off on 15 and 16 because we're going to do that in the chain rule section. I'm still getting used to this text. I didn't realize they were going to cover it in the chain rule section, so I put it in here, but we'll just postpone. All right. I do want to show you a little bit where we're going with this. In Calculus 1, we said that a function was differentiable if we could compute the slope of its tangent line. In Calculus 3, we're going to say that a surface, in this case we've got a surface in R3 where the third variable is a function of the first two. We're going to say it's differentiable if it's possible to compute not a tangent line, which we've already seen we can do in a lot of cases, but compute what's called the tangent plane. We're not going to deal with the tangent plane today, but I wanted to show this to you because it's a good time to talk about it. Notice that for the tangent plane, here you've got the curve of the surface running this way in the x direction, and then the curve of the surface running this way in the y direction. And we've got this is the direction. Oops, this is the derivative. This is the derivative here, and this is the. So sorry, that has to do with the partial derivative of f with respect to x. This has to do with the partial derivative of f with respect to y. And if I treat those derivatives as giving me vectors, then I've got two vectors in the tangent plane. Don't worry about this. I'm just pointing, I'm showing you where we're going soon. We'll worry about this another day. Okay? But there is this question of can I come up with a tangent plane? Put another way is there a plane that approximates the surface? Okay. So in Calc 1, folks, they said, okay, to be a tangent line basically means if you zoom in close enough, if you zoom in on this, essentially what you have is the line of the curve and the tangent line, but there's so little difference between those two, it's like they're lying on top of each other. Do you remember that idea from Calc 1? Okay. And I always, when I'm in Calc 1, I always give the students this example. I say that's sort of like, we're standing on the Earth, which is certainly a sphere. Let's be careful. Like it says, certainly a sphere or a ball, I guess. But we're on the surface of it, which is a sphere. And yet, when we look at a map, unless it's a very large map, like a map of the world, when we look at a map of a small location, we represent that sphere on a two-dimensional plane, the plane of the map. Because if you zoom in close enough onto the Earth, onto this surface of the Earth, you could imagine this section of the Earth being just a flat plane rather than being slightly curved. Okay. Now, if you do a large enough map, you got to start taking into account the curvature of the Earth. But for small distances, a plane, meaning a map, can represent the surface of a sphere. Okay? That's because a sphere is differentiable. It's a differentiable shape. Okay? So here we have the criteria for differentiability. I don't really want to get into this too much right now. except to say that there's another way we could represent this, and that's to say that z minus z naught is equal to partial f partial x times x minus x naught. That should be evaluated at a point, a, b. Plus partial f partial y evaluated at the point a, b. I need to give myself a little more room here. Times y minus y naught plus two other components, epsilon 1 times x minus x naught plus epsilon 2 times x minus x naught. Or excuse me, y minus y naught, excuse me. But these two terms, to be differentiable, means that these two terms go to 0. And although it may not look like it, this is enough. So I can rewrite this as z minus z naught is equal to a. Let's not use a because I got ab. Let's call it n1 times x minus x naught plus n2 times x minus or times y minus y naught. And there's an understood 1 in front of here. What's that the equation of, folks?
To the line.
Not a line.
A plane.
Plane.
Yeah, it's the equation of a plane. Okay. So you can see that basically what this is it's a plane with some little minute differences in the x and y direction. It's off by a little bit. That should make so what we're saying is a surface is differentiable if you zoom in close enough in such a way that these two components go to 0, the surface can be re-represented by a plane. Okay. That's sort of all I want to do with that for right now, but we do need this definition of differentiability. Okay. By the way, if you're looking for a definition that extends to all sorts of functions, so right now we're looking at functions that go from Rn to R. But if you want a definition of differentiability that works for all functions, that maps from 20-dimensional space to 30-dimensional space, something like that, this definition of differentiability is extendable. Okay? To higher, to not just higher dimensions, but to any sort of mapping. And so this is kind of the ideal. This is a concept, differentiability. Now, I'm not saying a derivative, but a concept that that you can extend to higher dimensions. Okay. This is where we start getting that more important definition of what we mean, sort of by something like a derivative. All right. Okay, I'm going to postpone this example. If I don't get this example, I won't hold you responsible for it. But let me just say that there are these two ideas that carry over from Calc 1. Okay. If you're looking at a function that's not continuous, there's no way it can be differentiable. Right? Here I've got the absolute value function right here. What's the slope of the tangent line at x equals, say, 2? You can't draw a tangent line to it. It's not continuous, so it doesn't make sense to ask a question about its derivative. So, say it one more time. If you're not continuous, you can't be differentiable. Now, just because you're continuous doesn't mean you are differentiable. So, for example, this curve right here with a cusp in it at x equals, say, 2 has a cusp in it, and you saw in Calc 1 that the derivative did not exist at a cusp. Is that function continuous at the cusp? It is continuous, but it's not differentiable. So being continuous is a necessary, so this is the math term, being continuous is a necessary but not sufficient requirement to be differentiable. Meaning, if you're not continuous, there's no way you're going to be differentiable. But just because you are continuous doesn't mean you will be differentiable. If I've lost you on that, here's an example. To live in Denver, you must also live in Colorado. So if I tell you that somebody lives in Denver, you also know they live in Colorado. But if I tell you somebody lives in Colorado, is that enough to conclude that they must live in Denver? No. Okay. So that's that whole issue there. Differentiability is a necessary but not sufficient condition. Excuse me. Being continuous is a necessary but not sufficient condition to be differentiable. However, we do have this nice little theorem here that says if the partial derivatives exist and they are continuous, then you'll be able to construct a tangent plane there. But there are cases where you can find the derivatives, the partial derivatives, and not be able to construct a tangent plane. All right, that's a real subtle point. It's an actually very important point, but I want to move on. Okay. So if you have questions about that, I'd love to talk about it more. I'm going to not, I don't think I've got any questions that hold you responsible for that. So you will get a chance to work an example like this in my math lab, and you will see that even though it's not differentiable at 0, 0, you can still compute partial f partial x at 0, 0, and partial f partial y at 0, 0. All right. Folks, I want to get started on this so we can hit the ground running next time. There was the chain rule in Calc 1. Really cool rule. It opened up a whole wide variety of problems you get to do. Okay? Really, the way you can think about the chain rule is doing successive functions. Okay? The chain rule is a rule for compositions of functions. And because we're dealing with multivariate functions, these can be far more interesting than they were before. Okay? That means that sometimes computing the chain rule for multivariable functions can be kind of difficult. Okay? Now, what you can often do is just do a bunch of substitutions and compute it by brute force. But that's not what we're trying to teach in this section. In this section, we're trying to teach a very, I can't say it other, kind of a pretty way of dealing with the derivatives of chain rules rather than using ugly brute force on it. Okay? So, all of these, I think, are made easier if you draw a tree diagram. So please, raise your right hand, solemnly swear to always draw a tree diagram for one of these chain rule questions. Thank you, thank you. Okay? So, here's what I recommend you do. Okay? W is a function of 3 variables. So I'm going to write W at the top and then give the variables that lead to W. So that's it's a function of variables x, y, and z. Okay? Each one of these is a function of both s and t. Now, you can get through most of this section without putting arrows on these trees. But I think, and so it's going to seem really redundant right now, but I could not figure out how to do this chain rule correctly I could do it for this example, but not for more complicated examples without drawing some directed arrows on this graph. So I would like to add some little arrows here pointing in the direction that the variables flow. These arrows are going to be redundant except for the very last 2 examples I do. They're not going to be, you're not going to think, oh, that's not very interesting. But eventually it will be important. Okay. Some terminology here. Let's do that in black. Some terminology here. W is the dependent variable. my s and t are my independent variables. And my w, x, y, and z are now called intermediate variables.
Sorry, W, X, Y, Z, or just X, Y, Z?
Oh, I'm sorry. My mistake. Yeah, you're exactly right, Hazan. Just x, y, z. Thank you. Good catch. Okay. Here's the picture of what's going on, folks. So if you like, and now so we could think of w as a function that maps from R2 to R. But really what we're doing is w is mapping, so that's just under, I don't have names for these functions, that's okay. But really another way to think about it is w is going to go from R2, it's going to move those variables into R3, and then move that result into R. So let me just draw a quick little picture that goes with that. So we've got the UV land, and we're going to map that into the XYZ land, and we're going to take that and map that into the W land. Okay. Now, there is a way to do some of, like I said before, there is a way to do some of these problems through brute force. However, often on tests, math teachers pick problems where if you try to do brute force, you're going to end up with a gigantic mess. And so this is the method that we want you to learn. It's the chain rule for multivariate functions, derivatives of multivariate functions. So I'm going to go ahead and compute partial w, partial s here. So what I do, the way I like for you to think about this is take your tree, go to W, and then backwards trace all of the different ways you can get to an S. Okay? And then because these are all rates of change, and rates of change are additive. Everyone know what I mean by that? If I'm going 20 miles an hour on a river that's going 10 miles an hour, what is my net rate of change? 30 miles an hour. What did I do? I added them up. Okay? Keep that in mind because that's what we have to do here. So I'm going to backwards trace all of the different ways I can get from W back to S. For example, there's one path. And there's another path. Okay? And then I'm going to add up all of those different ways. So I'm going to say that partial W, partial S is tracing the first one back. So let me take the second one off here. Ooh. No, I can't erase that second one. I'm going to trace this one back. So first I'm going to go backwards to here, and then I'm going to go backwards to here. So I'm going to take partial W, partial X, and then multiply that by partial X, partial S. Okay. So that says we're going to take how W depends upon X and then multiply that by how X depends upon S. Now there's a nice little visual way to see that you did this correctly. You cannot cancel these, but if you were to, do you see that that now looks like partial W, partial S? That's a little visual cue that you're on the right track there. Okay. I'm going to add to that all the other paths that can take me from W back down to S. So I could take partial W, partial Y times partial Y, partial S. Or I could take partial W, partial Z times partial Z down to S. And what have I done? I've added up the three different ways I could trace from W down to S. Notice that formally, although you can't actually do this, you know that you're on the right track because all of these essentially look like partial W's, partial S's. I think I've got a question there. Cedric, do you have a question? Oops. Oh, you're on mute, though, I think. Let's see here. Oh, okay, I'm sorry. Sorry about that. Okay. So let's do this again. No, we can't. That starts the chain rule. Okay. Folks, I'm trying my best here. Oh, let me stop the recording.